Hello, please somebody reply. Can you hear me?
Yes, sir.
Thank you. Okay, thank you. Good evening, everybody. I am Venkat Subbareddy, a research scholar at University of Hyderabad. So I am here to teach you some assignment problems of the course Matrix Analysis with Applications. Let me wait for a minute. I think people are still joining. I think you can see the presentation. So let me start the today's class. Actually, this is not your current assignment, week 2 assignment. This is some last year's assignment. What we have to do is we have to solve similar problems in that syllabus, not current week syllabus, assignment problems. So I'm solving previous year assignment problem, but unfortunately in the last week I had to solve this current course assignment problems only. So from now onwards I will solve previous year's assignment problems only. So I'm attaching the assignment question paper here. You can see, I'll upload this in Google Drive. You can see after this class. Anyway, I am presenting here, so you can see now also. So here also, then we have 10 questions, 10 problems. On each problem have 4 options. We have to solve this. These are just similar to that assignment problem, current assignment problems only. So let me solve the first assignment. First problem here. So first problem, it is which of the following function is a linear transformation. So it is given 4 options and it is asking to check which one is linear transformation. So before solving this problem, state let me give you one statement which will be useful to solve this. So today date is 9. I'm writing one statement. When t from v1 to v2, v1 v2 are two vector spaces. When t is a linear transformation from vector space v1 to v2, then we have t of 0 has to be 0. This holds always whenever t is a linear transformation. By using this, we'll solve two options here. So let me show you the question once again. So the first option is t from r cube to r square from such that t of x comma y comma z equal to x plus y plus 1 comma y plus z plus 2. So let me write this. Option A is t from r cube to r square such that t of x comma y comma z equal to x plus y plus 1 comma y plus z plus 2. So we have to check this is a linear transformation or not. This is a function. We have to check it is a linear transformation or not. So by using that statement which I stated above, we can check this. So when if t is a linear transformation, it should satisfy t of 0 has to be 0. But let's see what is the image of 0 under this function. So here t of 0 is nothing but t of the odd triple pair 0 comma 0 comma 0. According to the function definement, we have this equal to 0 plus 0 plus 1 comma 0 plus 0 plus 2, that equal to 1 comma 2, but which is not equal to 0. But whenever t is a linear transformation, we should have t of 0 has to be 0, but this is not happening, so we can eliminate the option 1. So 1 is not the correct option. Sorry for this disturbance. Second option is t is from matrix vector space m2 cross 2 to m2 cross 2. T is from m2 cross 2 to m2 cross 2 such that t of a equal to a minus I. Here I is identity matrix, so we have to check this linear transformation or not. We use the same statement above. So here matrix in this vector space is in this vector space the zero matrix is nothing but zero element is nothing but zero matrix. That means 0 comma 0 comma 0 0. The image of this under the definement of the function is 0 0 0 0 minus the identity 0 1 0 0 1, which is equal to minus I. But in this vector space m2 cross 2, this is not the zero matrix, so this function is also not the linear transformation. Okay. So this is also not a linear transformation. Now we will check the third option. C is from 0, t is from c of 0 comma 1 to the same vector space such that t of f equal to integration 0 to 1 f of x dx. T is from c of 0 comma 1 to c of 0 comma 1 such that t of f, where f is continuous function from defined on the interval 0 to 1. I think you know the definition of c of 0 1. So we have to check this is a linear transformation or not. For this option we will directly proceed with the definition. So what we have to check is to check whether the function is linear transformation or not, we will take two functions f comma g belongs to that domain. Here domain is nothing but c of 0 comma 1, and we will check whether t of f plus g equal to t of f plus t of g or not. So by the definement of t, we have this equal to integration 0 to 1 f of x plus g of x dx. So this we can write because integration is integration satisfies distributive law, so we can write this f equal to integration f of x dx plus integration g of x dx. So you can see this is equal to, by the definement of t, we have this is equal to t of f plus t of g. And similarly we have to take f one element in the domain and one I'm seeing the element alpha as scalar, is a scalar. So the another property of linear transformation what it should satisfy is t of alpha f, it should be equal to alpha times t of f. So by the definement of t, we have integration 0 to 1 alpha times f of x into dx, that equal to alpha times integration 0 to 1 f of x dx, f of x dx, that equal to alpha times t of f. So from these two equations we can say T is a linear transformation. Therefore T is a linear transformation. But of course we have to check the option 4 also. C is the correct option here, but we will check the option 4 also here. The function defined here is T of ax square plus bx plus c equal to a plus 2 times x square plus 2b plus c into x plus a minus c. So for this, let me write the linear transfer. Let me write the function here. T of a comma b comma c equal to a plus 2 times x square plus something. What is it? 2b plus c a minus c. 2b plus c times x plus a minus c times 1. I'm not writing 1 here. So to prove this as linear transformation, we have to, let's, is this correct? Linear function, sorry, left side ax square plus bx plus c. So we'll check here that t of 1 plus t of x equal to t of 1 plus x or not. Why I am doing this? Because for the vector space given here in the option, that the vector space is P2, that means polynomials of degree at most 2. For this vector space we have a basis, standard basis 1 x and x square. So I'm just checking for the first two elements 1 and x. You can take another two elements also, any of the another two elements also. I'm just checking this. So we have, by the definement of t of 1 equal to 2 times x square plus x plus, sorry, minus 1. Similarly t of x equal to 2x square, b is 1, so 2x plus 0. It should be, the sum of these two elements has to be equal to t of 1 plus x. Firstly let's check what is t of 1 plus x. So by the definement of t, again we have this is equal to 2x square plus 3x plus, sorry, minus 1, but which is not equal to t of 1 plus t of x. So you can say t is not linear transformation. So from these calculations we can say t is a t given in the option C, from c of 0 comma 1 to c of 0 1, such that t of f equal to integration 0 to 1 f of x dx. This is the only linear transformation among these options. It is given the option also here, you can see that. Now let me solve the second problem. So the second problem is given a real vector space W and spanned by the vectors u1, u2, u3 and u4. Then it is asking what is the dimension of W. So firstly let's write the combination of given vectors in matrix form. I'll tell you how to solve this problem. Firstly let me write u1 equal to 1 comma 2 comma 1 transpose, u2 equal to minus 1 0 comma 3 transpose, u3 equal to 2 comma 1 comma 1 transpose, u4 equal to 0 comma 1 comma 1 transpose. So it is given that W is subspace of R cube spanned by U1, U2, U3 and U4. Now it is asked to find dimension of W. So let me write the given vectors in matrix form. Then we will convert the matrix into row echelon form, and we will see what is the rank of that matrix. 1 2 1 minus 1 0 3 2 1 1 0 1 1. So to convert this matrix into row echelon form, we have to make the elements below the diagonal as zeros. We have to make these elements, the elements in the red mark, we have to make all, so this element also. So this is diagonal. We have to make the elements below that diagonal are zeros. Sorry, again wrong. We have to make all these elements as zeros. Then we can see the rank of this matrix. So for this, I think you can, the people who attended in the last class can understand this easily. So firstly, I'm making the element -1 as 0. For this, I'm just multiplying this with R1 and this with R2 and doing the row operation. That is, we are converting R2 to R2 plus R1 because the signs are different. It's if we add those two becomes the element -1 will become 0. So here the first row will remain same, the second row will become 0, this is 2, this is 4, and here we can do the another operation also same directly, so that we can reduce the number of calculations. So for R2 I am doing, for R3 I am doing this operation. So what is the operation here is R3 minus 2R1, because the signs of the two elements are different, so I am subtracting it. R3 minus 2R1. So for this row operation, the third row will become 0. Here R3 minus 2R1. 1 minus 4 minus 3. This is minus 1. And for the fourth row R4. Similarly, we have the row operation. So no need to do, because we already have the element 0 there. So I am not doing anything for the fourth row, and simply writing the same row here. So still we have to make 3 more elements as zeros. Let me mark those. These 3 elements we have to make as zeros. So for this, what are the row operations I am going to do are R1, R2, R3. So here I am using the second row because we already have here the 0 elements. So whenever we do the row operations with the R2, this element, these two elements will not get changed. If we use R1 row, these two these two 0 elements will become non-zero, but that's not what we want. So I'm using here the R2 operation, R2 row to do the operations, and the operations are here, this thing and this thing, and we have to add the operations. So R3 will become R3 will become 2R3 plus 3R2, and similarly R4 will become R4 2R4 minus R2. these two row operations will result 0 to 4. So here R3 will get changed and it will become like 0. This becomes 0. 2R3 plus 3R2. This is minus 2 plus 12. This will become 10 and here 0, 0, 2R4. 2 minus 4. This is minus 2. So we still have to make this element minus 2 as 0. For this I am doing just using R3. So here what I am doing is this row operation. So the row operation is R4 is converting into 10R4 plus 2R2, or even we can use the another row operation, which this is similar to 5R4 plus R2, because we are just making this element as 0, this element as 10 and subtracting, adding to the third row. So for that it is just enough to multiply the fourth row with 5 and third row, sorry, this is R3, and it is enough to multiply the fourth row with 5 and adding it with third row. We can do any row operation here, we will get the same matrix. It will become, sorry, let me write there only. So it will become 1 2 1, 0 2 4, 0 0 10, 0 0 0. So from this we can see the rank of this matrix is rank equal to 3. So firstly what we did here is, firstly we have written the given vectors into matrix form and then we have calculated the rank of that matrix. So from this, how we can conclude the rank of the given vector space is rank of W equal to, sorry, this is dimension of the subspace W equal to the rank of the matrix corresponding to the generators of W, and that is nothing but 3. So rank of W is equal to 3. Sorry, again this is dimension. Dimension of W equal to 3. This is second problem. So the option is given here is 3. So let's see the third problem here. So it is given a vector space V of all polynomials having degree at most 3. That means the polynomials should be of the form. It is given that indirectly V is a vector space of the polynomials ax cube plus bx plus cx plus d, where a, b, c, d are real numbers. So this is the vector space given, and given two subspaces W1 and W2 as this. W is the polynomials in V, and under which P of 0 has to be equal to 0, and similarly W2 P of 1 has to be equal to 0. Now it is asked dimension of W1 intersection W2. Let's see what is the how to do this problem. So given V equal to ax square plus bx plus cx x cube plus bx square plus cx plus d, such that a comma b comma c d belongs to R, and W1 equal to P belongs to V, where P is a polynomial, P of 0 equal to 0, and W2 equal to P belongs to V, such that P of 1 has to be equal to 0. Now it is asked dimension of W1 intersection W2. W1 intersection W2. So whenever a polynomial should be in w1 and let me write that. Let p of x belongs to w1 intersection w2. That means p of x has to be in w1 and p of x has to be belongs to w2 also. What it is asked here is, what is the dimension of the polynomials p of x whenever p of x belongs to w1 intersection w2. So let me consider in a general form of polynomial p of x equal to ax square plus bx plus x cube plus bx square plus cx plus d. So whenever p of x belongs to w1, we have p of 0 equal to 0 and p of 1 also equal to 0. P of 0 equal to 0. Let me write it clearly. Let this polynomial belongs to w1 intersection w2. That implies p of 0 has to be equal to 0 and p of 1 also has to be 0. That implies from this we can say d equal to 0, and from this a plus b plus c equal to 0. Anyway, we have already d equal to 0. So from these two, what we can conclude is d equal to 0 and a equal to minus b minus c. That means what is the general form of the polynomial p of x is, that implies p of x has to be equal to a times x cube plus, sorry, here let me write in another form. Here let me write c equal to minus a minus b. We can take that a equal to minus b minus a also, but this is simpler to do calculations, so I'm just taking this bx square. We have c is minus plus minus a minus b times x and d equal to 0. That means p of x has to be equal to, if we take a as common, x cube minus x plus b here x square minus x. So what we have here is, any polynomial which is in w1 intersection w2, p of x should be in the form p of x has to be in the form some scalar times x cube minus x plus some scalar times x square minus x, because we already have here a and b belongs to R. So the dimension of w1 intersection w2 is, here is 2, and w1 intersection w2 is equal to span of the vectors, two vectors x cube minus x comma x square minus x, that you can see here from here. This is third problem. So the fourth problem is, some of the following set does not form a vector space. So given some sets over some fields are some fields, so we have to check which one is the vector space. So the first option here is the set of all n cross n real symmetric matrices over R. That means the first option is, this is equal to A such that A transpose equal to A. We have to check this set is a vector space or not. This is for the problem. So the first option is the set A such that A transpose equal to A over R. We will directly check the properties of the vector space. So whenever to prove this as a vector space, we have to check two properties. That is, one is whenever two elements, let me call this set as V1 so that we can use that notation. So we are taking two vectors, two elements in V1, and to prove the vector space we have to check that A plus B belongs to V1 or not. This is first property. And similarly, whenever alpha belongs to R and A plus B, single element here, A belongs to V1, we have to check alpha times A belongs to V1 or not. I think one can check this easily. So let's take A and B belongs to V1. That implies we have A transpose equal to A and B transpose also equal to B, because those two are symmetric matrices. So now we have to check is A plus B whole transpose equal to A plus B or not. So by the property of transposition, what we have is this is equal to A transpose plus B transpose. So this is equal to A plus B. Similarly, we can check alpha times A whole transpose. This is equal to alpha times A transpose. This is equal to alpha times A. So we have, by these two properties, we can say V1 is a vector space. But the question it is asked here is which one is not a vector space. 1 minute. Here you can see which of the following set not a vector space. So the first option is not correct because it is a vector space. The second option here is the set of all real continuous functions on 0 1 under usual addition and scalar multiplication. Here this is also direct direct option, so one can check this easily. Second option is C of 0 comma 1. So let's take two elements in this. F comma G belongs to C of 0 comma 1. And alpha belongs to, alpha is a scalar. So what is the option? So by this we can directly say whenever f and g are two continuous functions, we have f plus g is also continuous function. So f plus g belongs to C of 0 comma 1 because sum of two continuous functions, addition of two continuous functions is continuous and scalar multiple of continuous function is also continuous. So therefore C of 0 comma 1 is also a vector space. You can see this in previous options, but here it is not given directly. The real continuous functions is nothing but C of 0 comma 1. So that if you can see that it is already given here, it is a vector space. Here similarly in the third option also by the same calculations as of option 2, we can say that third option is also vector space. Here in the fourth option, let's see what is happening. The third option Q of x is also a vector space by similar calculations. But in the fourth option, it is given that determinant of M has to be equal to 0, where M is a matrix. All 3 cross 3 matrices M with the determinant of M has to be equal to 0. So we have to check that whenever determinant of two different matrices are equal to 0, then the sum of that two matrices, determinant of that sum of two matrices is also equal to 0 or not. Let me write the set clearly, then you can have some idea. So it is given that V4 equal to set of all matrices M 3 cross 3 such that determinant of M equal to 0. Sorry, this has to be inside. So this V4 set is a vector space or not over R. So let me take two matrices A comma B belongs to V4, and we have to we have to check that determinant of A plus B equal to 0 or not. Simply we can take A equal to 1 matrix 1 0 0 0 0 0 0 0 0 here, and another matrix has 0 1 0 0 0 0 0 0 0. Why I am taking these two matrices here only? Because for the given set M, actually this is a subset, the given set is a subset of the vector space. What is that called? Vector space of the all matrices of order 3 cross 3. So for this vector space, we have 9 basis elements. Those will looks like these two elements and some more elements 0 0 1 0 0 0 0 0 0. Likewise, we'll get some 9 elements. Those all forms a vector. Those for all 9 elements are nothing but basis of the vector space of all matrices of order 3 cross 3. So I'm just considering the first two elements here. You can take any of those two elements and let's check the sum of those two elements contains in the vector space or not. So here A plus B is nothing but, here we can check determinant of A equal to 0 and determinant of B equal to 0. That means determinant of A equal to 0 and determinant of B is also equal to 0. That means A comma B belongs to V4. But we have to check whether A plus B belongs to, here A plus B also belongs to V4. But let me change some matrices here. Here let me take 1. Here it is 0. Here it is 1. I'm just changing the matrices. Actually, there exist infinite number of matrices for which A plus determinant of A equal to 0 and determinant of B equal to 0, but determinant of A plus B is not equal to 0. These two are just one pair of those two matrices, collection of those kind of matrices. So here A plus B is nothing but 1 0 0 0 0 0 1 0 0 0 1. That implies determinant of A plus B equal to 1, which is not equal to 0. That means A plus B does not belongs to V4. That implies therefore V4 is not a vector space. The options for the problem it is asked is which one is the not a vector space. So the fourth option is the correct option. It is not a vector space. The remaining three options are vector spaces. This is also a vector space. This is also a vector space. So the fifth problem here is, given a vector space V over a field F and three vectors V1, V2, V3 belongs to V, and given three subsets S, T and W of V as T S equal to V1, V2, V3, T equal to V1 plus V2, V1, V2, V3 and v1 minus v2 plus v3. Similarly, w equal to v1 comma v2 minus v1 comma v3 minus v2 plus v1. So the options here are span of s equal to span of t or not. Here also it is asked to check whether the statement is true or not. So for the first option we can check this easily, because we can see the given set in the given set T. This contains the elements which are, every element is spanned by the elements v1, v2, v3. So we can simply check that span of S equal to span of T. And one more property I want to state here is, when b1 and b2 are two different bases of a vector space, then we have the cardinality of b1 has to be equal to the cardinality of b2. We use this statement to somewhere for the remaining options. So let's see the option B. Here it is also similar as option A, because the set W, it is also it also contains the vectors which are linear combinations of the vectors v1, v2, v3. So span of S is equal to span of W. But in the, sorry, these two are wrong options, because it is asked to calculate, to check incorrect option. So in the third option, if S is a basis of V, then T is also a basis of V. So here we use this statement. This statement. So suppose this statement is correct. That means the cardinal, by this, suppose the option C is correct, then by this statement we have the cardinality of S is equal to cardinality of T. But you can see the cardinality of S is 3, but the cardinality of T is 4 here, because in T we have 4 vectors v1, v2, v3, and v1 minus v2 plus v3 also. So by this statement we can say, here we have cardinality of S equal to 3, but cardinality of T equal to 4. So from this we can say cardinality of S not equal to cardinality of T. But whenever S and T both are bases, then we should have the cardinality of those sets also, those two sets are same. But here it is different. So we can see the third option is incorrect. Similarly, in the fourth option, if S is a basis of, we are by the second option we can check this fourth option, but we can check this option. If S is a basis of V, we can say span of S equal to span of W, that equal to, that means W also is a basis of V. I'm not writing here, it should not looks good. So from the second option we can say whenever S is a basis of V, then W is also basis of V. So fourth option is also correct, but according to the statement it is asked, the fourth option is incorrect. That is about fifth problem. The sixth problem here is, given a basis alpha 1, alpha 2, alpha 3 of a vector space W, and it is defined a linear transformation T and V such that this happens: T of alpha 1 equal to alpha 1 plus alpha 2, T of alpha 2 equal to alpha 2 plus alpha 3, T of alpha 3 equal to alpha 3 plus alpha 1. Here it is asked is which of the following is correct. Here it is asked the correct statement, but in the above two problems it is asked incorrect statement. So here let's check which option is the correct option. So let me write the options, let me write the problem clearly. This is sixth problem, I suppose. Given a vector, given a set alpha 1, alpha 2, alpha 3, this set is a basis of vector space V and T from V to V is a linear transformation defined as T of alpha 1 equal to alpha 1 plus alpha 2, T of alpha 2 equal to alpha 2 plus alpha 3, comma, T of alpha 3 equal to alpha 3 plus alpha 1. Let's see the options what we have to check. So the first option is T is 1 1. So to prove T is 1 to check whether T is 1 1 or not, we have a property that a linear transformation, let me write clearly, a linear transformation T on a vector space is 1 to 1 if and only if kernel of T is equal to singleton set 0. So to check whether T is 1 1 or not, here we check that kernel of T equal to 0 or not. Let me check that. So let's take one element x. I'm naming it as x in the kernel of T. Here we will prove that the element x equal to 0. Then we can say kernel of T equal to singleton set 0 only. From that we can say T is a linear transformation. Sorry, from that we can say T is 1 1. So I have taken x belongs to kernel T, that means T of x equal to 0. But given alpha 1, alpha 2, alpha 3 is a basis of V. Here we have this is a basis of V. So we can write x as a linear combination of alpha 1, alpha 2, alpha 3. We can write x equal to a alpha 1 plus b alpha 2 plus c alpha 3, because alpha 1, alpha 2, alpha 3 as a we have that is a basis. So from this we can say T of a alpha 1 plus b alpha 2 plus c alpha 3 equal to 0. I'm just writing from this step. That means because we have T is a linear transformation, so we can write this equal to T of a alpha 1 plus T of b alpha 2 plus T of c alpha 3. That is nothing but a times T of alpha 1 plus b times T of alpha 2 plus c times T of alpha 3. These steps are coming from the definement of from the from the definition of linear transformation. If you studied the definition of linear transformation, you could understand this easily. What we have is these are equal to 0. So for this, by the definement of T, we have a times alpha 1 plus alpha 2 plus b times alpha 2 plus alpha 3 plus c times alpha 3 plus alpha 1. This equal to 0. So from this we can say, if we take alpha 1 as common, a plus c plus alpha 2 times a plus b plus c, alpha 3 times b plus c equal to 0, because we have alpha 1, alpha 2, alpha 3 are is a basis. So whenever the linear combination with the three vectors are 0, then we have the scalars are zeros, because that forms a basis. B plus c equal to 0. This is because alpha 1, alpha 2, alpha 3 is a basis. Basis means it is linearly independent. So from that property we can say the scalars has to be equal to 0. From this we can say a equal to minus c. From I'm directly writing this. Let me write this directly here. What from this what we can result is a equal to b equal to c equal to 0. This is how it is. Let me explain this. From the first equation we have a equal to minus c. So let's substitute this in second equation. So we can get minus c plus b equal to 0. And from the third equation we have c plus b equal to 0. So from this, by adding these two equations we have 2b equal to 0. That implies b equal to 0. So from this we can say c equal to 0 and a equal to 0. This is how a equal to b equal to c equal to 0. So what we have proved is we have that x equal to we have x equal to a alpha 1 plus b alpha 2 plus c alpha 3. This is equal to 0. That implies kernel t is nothing but singleton set 0. That implies t is 1 to 1. So from this property I am saying t is 1 to 1. The property here I use is this is one statement. Let me write clearly. This is one property of a linear transformation. So from this we can say t is 1 1. So this is the correct option. And let's check about the remaining options also. So for the second option we have that I am writing here only t of this is equal to that implies let me check the what is the value of left hand side. From that we can conclude t of alpha 1 plus alpha 2 plus alpha 3 that equal to t of alpha 1 plus t of alpha 2 plus t of alpha 3. From the definement of t we have that we can check this is equal to 2 times alpha 1 plus alpha 2 plus alpha 3, but it is not equal to 0 because we have that alpha 1 plus alpha 2 plus alpha 3 is a basis, so its sum cannot be equal to 0. How I am saying is because whenever it is a basis it has to be linearly independent, so the sum cannot be equal to 0. So from this we can see the option 2 is wrong. Similarly one can check the values of t, the values of this thing on the left hand side and the expression in the right hand side, both are not equal here also and in the fourth option also. This is not difficult, so one can check this easily. So I'm directly going to next problem. So here it is given that t is a linear transformation from m2 cross 2 to r cube given by t of a b c d equal to 2a comma b plus c comma d. So it is asked to calculate the basis of the range of t and the kernel of t. Let me write this. For b, c and d, check the calculations. This is about sixth problem. How we can eliminate the remaining three options. So let's see the seventh problem. T is given from m2 cross 2 to r cube given by t of a b c d equal to 2a comma b plus c comma d. I think let me check this once again. 2a comma b plus c comma d. Okay. So it is asked to calculate the range of t sorry, the basis for range of T and dimension kernel of T. So firstly let me check the range of T. So here we can easily change, we can easily see that range of T is nothing but the collection of the elements 2a comma b plus c comma d such that a comma b comma c comma d belongs to R. So it is enough to calculate the basis, it is enough to calculate the basis for this set. So we can write any element of the form we can write any element of the form 2a plus b plus c comma d. Yes, I'm just taking the elements a b c and d as common. So we can write this as a linear combination of a times 2 comma 0 comma 0, because here we have the coefficient of a as 2, so I'm first writing the first coordinate as 2, and here we don't have in the second coordinate and third coordinate we don't have the element a, so the coefficient of a here is 0 and 0. Similarly we will write, similarly the element given is some addition of b times 0 comma 1 comma 0 plus c times 0 comma 1 comma 0 plus d times 0 comma 0 comma 1. This you can check easily. So from this you can say 2 comma 0 comma 0 comma 0 comma 1 comma 0 comma the third element is also same 0 comma 1 comma 0 and 0 comma 0 comma 1 generates range of T, but it is asked to find the basis. Basis is different from generators. So here what we have is these two elements are same, so in the basis elements we cannot write two same elements, so we are simply writing this as 0 comma 1 comma 0 0 comma 0 comma 1 is a basis of T, because this is one basis of T, but in the given options it is, this set is not there, you can check that. So actually this set is similar to that set what we have done. These two sets are same, but of course we have to check, we have to see about the kernel also. But instead of one here we got the 2, because whenever a is a scalar, let me explain how it is. Here we can say instead of here, let me write with red, you can understand. So instead of a here, if we take a by 2, sorry 2a times 1 here, then we will get 1 here, here also 1. So then in that case also this is a basis. what I, what I mean here is, just because of the scalars we can say this set is also a basis, and the earlier set containing 2, that is also a basis. This just depends on the scalars. So we can say 1 comma 0 comma 0 0 comma 1 comma 0 0 comma 0 comma 1 is a basis of range of, here also it is range of T. Not only this set, actually there exists infinite number of infinite number of sets. Instead of here we can take 3, 4, anything. Here also we can take 5, 6, any element. That forms a basis. But according to the option given, it is a basis of range of T. So now let's see the kernel of T. So to calculate the kernel of T, let's take some element x belongs to it is a matrix, right? So let me write A belongs to M 2 cross 2 and A belongs to kernel T. Now we have to find out in which form A is. Since A belongs to kernel T, we can say T of A equal to 0. Let's write the general form of the matrix A, that is nothing but A, B, C, D. From the definement of this, we have from the assumption of A, we have this is equal to 0. So from the definement of T, we have that this is equal to 2 times A, B plus C equal, comma, D. This is T equal to 0. So from this we can say 2A equal to 0, B plus C equal to 0 and D is also equal to 0. So from this we can say again A equal to 0, comma, B equal to minus C and D equal to 0. So let's substitute these values in general form of the matrix A. What we get is, from this we get A equal to 0, 0, B, C is nothing but, from this we can say minus B, 0. So that means it is nothing but B times 0, 1, minus 1, 0. So that means the only matrix 0, 1, minus 1, 0 generates the kernel T. That means what these calculations, from these calculations what we can understand is, whenever A is in the kernel of T, if A belongs to kernel T, that implies A has to be a linear combination of this matrix 0, 1, minus 1, 0. That implies kernel of T is nothing but the collection of the elements. Let me write B only, B times 0, 1, minus 1, 0, such that B belongs to real numbers. So from this we can say the matrix 0, 1, minus 1, 0 is the basis. Let me write in the matrix set form, is the basis of kernel T. From these two, let's see which option is correct. So from these two, from range of T, we can say this set is basis for T. So from the range of T, and from kernel of T, we can remove this. This is not the basis for kernel T, and this is the correct option. So this is the correct option. You can see that here. I think time is over. We'll stop here. Similarly, the remaining problems also simple. By using the definition of linear transformation for this 10th problem, by writing the linear combination of by the definition of T, we can write this is equal to 2 times this element. We can write this as 2 times T of E1 minus 3 times T of E2 plus T of E3. So by the definement of T here, by doing a simple addition and subtractions, one can get the option, one can get the answer. Here it is given the answer also, one can see that easily. Here also, by writing these two vectors in matrix form and checking the rank of that matrix, we can conclude the rank of T also, because the rank of T is nothing but the rank of the matrix corresponding to that linear transformation. We'll get some answer as to that, one can do easily. Here also it is simple. So it is asked to find the dimension of null space. Null space is nothing but the collection of elements whose image under T is 0. That means we have to calculate we have to assume T of A comma B comma C equal to 0, and we have to find the values of A, B, C. From that we can conclude the null space of T. I suppose from this we can say A equal to 0, A equal to B equal to C equal to 0. So from this we can say null space is, dimension of null space is 0. This one can check easily. That is how to solve the remaining problems. Lack of time, I could not solve this. Does anybody have still doubts in these problems?